Okay, so we continuing our session, and next presentation is by Bedassa, Regassa, Cheneka from Agricultural Transformation Agency in Ethiopia. And here it's a talk on some added value for downscaling of seasonal hindcasts.
Shall I start? Okay. Okay. Good morning, everybody. I'd like to present my research on research added value of precipitation downscaled on seasonal hindcast of West Africa downscaled by COSMO-CLM using MPI-ESM. So I'd like to thank the organizer of the conference for inviting on this workshop. And this research work is done at Deutscher Wetterdienst, which is sponsored by Alexander von Humboldt as fellowship in 2013-14. So this is the outline of the presentation: background, study region, data and the methodology, objectives, result discussion, finally conclusion. So currently, climate information is very important, especially the prediction of it is a very core task for climate scientists to improve the seasonal prediction skill. Predictability in seasonal climate prediction is influenced by different climate system scales by global, regional, and local, just like water bodies and the topographic features. So regional climate need to improve the simulation of a small scale present in the climate model. So to improve this regional climate model, we have to look into added value. The first one is real added value, just comparing the simulated climate model with observed data. And the second one is potential added value, just to see how much the small scale is present. That is by aggregating the high resolution into low resolution climate model. So the objective is to look the performance of climate COSMO-CLM in the MPI-ESM model to evaluate the spatial bias of the climate model of West Africa, to investigate the precipitation frequency distribution over different scales to look extreme precipitation, and finally to look the real and the potential added value, which was discussed in the earlier presenters. So the initial boundary for the COSMO-CLM is used MPI-ESM, and the simulation is from 2000 to 2009, from May to September, and the analysis is just considered June to September. And to evaluate the performance of the model, we have used different graded precipitation, GPCC, ARC2, TRIM version 7, and TAMSAT are used. And we have the methodology, we have used spatial and temporal analysis, as well as potential and real added value. So this is the result observed. Just we have considered different regions, especially the EN and the ES is the area which have high topography, and this SS in the region is very maybe low topography. So the red one is, which is the CCLM, COSMO-CLM. If you see over EN, the COSMO-CLM is overestimate comparing with other global climate model as well as the, with other grid data set. And in the second ES region also, it's similarly, we can see especially the standard deviation of the CCLM is very high compared with the other regions. And over SS and over the 4 region, we can see that over most of, in most of the months, in June, July, August, September, the standard deviation of CCLM is just overestimated than the other with global model as well as the gridded data precipitation. But comparing the 4 region, the high frequency COSMO-CLM is highly overestimated over the high topographic region over EN. And this is also the standard deviation. And we can see the temporal variability is maybe captured, especially over Ethiopia. We will see the 2002 and the 2009 is the dry years. So almost those years may be relatively captured by the models. And 2006 is known as the wet years, and this wet years also captured by the models. Looking at the spatial base, if you see the area nearly to the EN over that is high topography region, the model, both the COSMO-CLM and the MPI is highly overestimated, while over the other region, especially the region which is circled by the red color is where the both COSMO-CLM and the MPI-ESM global model is underestimated. This is generally maybe with local scale or small scale features. That is maybe those overestimated area is that is high topographic area, mountainous area. So looking the different regions, that is root mean square error and the base. If you see the first one is just the COSMO-CLM, and the second one is the MPI-ESM root mean square and the bias. And if you see the compare it, in this case, in the case of regional climate model, COSMO-CCLM is just, it is overestimate. But in that case, the bias is, over most of the region is just negative bias. This is that the COSMO-CLM mostly shows the weight bias or positive bias, and also the root mean square error for COSMO-CLM is just a kind of overestimate comparing with global model. This is maybe due to local small scale features. So this is, I like to talk potential added value, which is just adopted from DeLuca and also presented in the earlier presentations. So this is just aggregating from low resolution to high resolution, from high resolution to low resolution. So it is in this potential added value that is the extreme precipitation value at a high resolution minus extreme precipitation value at low resolution. And the low resolution in this case, we take 3.72. So by normalizing this one, the added value, potential added value ratio to high resolution extreme, so we can say if this one is maybe close to 1, it is at added value. If it is maybe close to 0, it's the regional climate model have no added value. So in this case, we like extreme precipitation over multi-scale. This is not a virtual GCM just by aggregating from high resolution to low resolution. So we can see that the extreme precipitation at 95% is just reduced as we go from a high resolution to low resolution. So this is the same, and in the case of 60 days, it is highly reduced. That's averaging, it is just like the extreme precipitation is not well captured if we average the temporal resolution. It is the same for all the regions. So this is a potential added value. If you see this, the first one is relative potential added value in daily, and the second one is 60 days. And in daily, we have relatively high potential added value. In the 60 days, we have the potential added value is reduced. This is just to see where small scale features are present. That means if you can apply regional climate model, where we can get added value. That means especially over EN and ES is the high topographic region. So those topographic region, we can say that if you apply, we can get some added value from regional climate model. So this is the real added value, which is also mentioned in the earlier presentations. So by just mean square error between the GCM and observation minus climate, that's regional climate model in the observations. Just as first used by De Luca and laterally adopted by Dossel at 2014. So we can, the normalized is just between -1 and 1. And if this real added value greater than 0 means the regional climate model has added value, whereas if it is less than 0, it has no added value. So here we can see that especially using over different months, June, July, August, September, and the seasonal mean, with comparing with different different observed data sets, GPCC, ARC2, and the TRAM. So if you see the one which is blue and white color is no added value, and the other which has red, orange, and blue has added value. So we can see that over most of lowland area it has added value. What does it mean? That even if over topographic areas there are potentially added value, those small scale feature is not well resolved in this climate model. So lastly, my conclusion, COSMO-CLM overestimate precipitation compared with global model and observing the satellite gridded precipitation. COSMO-CLM has weight bias over high mountains region, where convection in the topographic features present and dry bias over lowland areas. Potential added value is highly available over highland areas. Looking spatial real added value is more seen over lowland area compared with highland areas. And this is maybe you can refer to just, this paper is published in 2016 on Advances Meteorology Journal. Yeah, that's all. Thank you very much.
Okay, thank you. So now we have time for a couple of short questions, if we have any. Okay, so in this case, maybe I can ask one question, because when we're using RCMs for downscaling seasonal hindcast, it's very easy to verify if we have any added value in terms of predictability. Because here it was not so much about, for example, the skill of RCM in predicting wet or dry summer. So are you going to do such kind of work as well? Or?
Yeah, I think we did this one just to see how added value, what you raised is also important.
But this added value is basically only about some kind of climatology. A little bit more. It's not in terms of predictability. That is most important for seasonal forecasting.
Yeah, exactly. Maybe we can refer from this spatial bias. If you see the spatial bias, it is compared with the observed data, so that we can see how much it deviates from the observation.
But as well, you have very big differences across different observational data sets.
Additionally.
So it's a problem. Okay, thank you. So we're moving to next talk by Filippo Giorgi from ICTP. So now we're moving to the European Alps, trying to find the added value there.
Where is it?
It's
No. Oh, yes, it's this. I don't know. Oh, one. Yeah, this one. Okay, so many things have been already said about added value, so I'm not gonna repeat them. I just wanted to mention a couple of common misconceptions about this issue of added value that I see very often when I get reviews of papers. The first one is that very often it is expected that RCMs should be better than GCMs for everything. This is not the case in general. We have seen that, but it's not even expected. There are some things where the RCMs are driven like large-scale 500 millibar heights, like René showed, or other large-scale fields where RCMs are not expected to be better than GCMs. RCMs are, in this context, downscaling tools, so they are expected to produce better fine-scale information. If this fits back to the large scale, maybe we can expect something, but this has to remember there's always the boundary forcing. The second one is that sometimes you show a picture where an RCM is worse than a GCM in the bias, you get the comment downscaling doesn't work. This is Obviously not true, because the bias could be there because that model doesn't work, not because downscaling doesn't work. But this is a misconception that I often find. So as René said, downscaling is a tricky issue. You actually need to look for it and need to really have a specific question where you actually look for added value. For example, if topography, extreme events is something where we expect added value, regional circulations, and so on. But the key question that was asked by somebody is, does this added value in present-day climate turn into added value in climate change? And that's the main question that I want to address today. I just want to show you this picture from René. He gave me a few years ago. I think this is the best example of added value. I was surprised he didn't show this. You remember this figure? I would advise everybody to use this if you want to show what we mean by added value by an RCM. But let's go to the talk. So what we did, we look at summer precipitation over the Alps. The Alps have very complex topography, so we do expect added values. We took a bunch of models in EURO-CORDEX and NA-CORDEX. In particular, don't ask me how we selected these. It was kind of a complex process, but anyways, at the end, we selected 5 RCM runs, 2 from NA-CORDEX, RegCM and Aladdin, and 3 from EURO-CORDEX, and 4 GCMs. Reference period, future period 2070, RCP 8.5, high-resolution observations to actually evaluate the model. The models are run over the big European domains, but we actually look at this region, which is the region where we have the observation data. First, you've seen many examples of this. This is the added value in present day. What we did is we interpolated all the fields onto 3 grids, a 1.32-degree grid, so sort of GCM scale, 0.44, 0.11. These are the GCMs for summer precipitations, the 0.44 RCMs, the 0.11 RCMs on the 3 grids. And this is the observed data set with and without an gauge undercatch correction. Just if you look at the downscaling, the downscale field to the fine scale, it's obvious, of course, that if you compare this figure with the observations, you actually get quite an amazing added value. You can see it by eye, but I think it's always nice to have some actual quantitative metrics. Taylor diagrams are perfect because you remove mean biases when you do a Taylor diagram. What you see here are Taylor diagrams for the 4 seasons, the GCMs, RCMs on the 3 grids. The key message here, if you actually check all these plots, you will see that the red dots are always closer to 1 than the black ones, and then the blue ones. The red dots are the 0.11 data, upscaled also at the 1.32 grid. This means that the finer scale models were the best, not only when downscaling, but also when upscaled at the GCM scale, which gives more robustness to the added value because it tells you it's not just a disaggregation thing, but it's also maybe capturing some specific processes, in particular, as we will see, for example, the topographic forcing of convection. We have seen a few of these. Oops. So I'm going to go fairly quickly through this. You can get much better PDFs. This is at 0.11. Again, observations is the red. 0.11 is the, green is the observations. Red is the 0.11 models, 0.44 models, GCMs. So you see obviously a big gain actually when you go to the 0.11 scale. In fact, there's at least one model that can replicate the observations very well. Incidentally, also the observations are scaled onto all these grids. But if you actually go to the 1.32 grid, I don't know if you can see it, but the black dots are actually the farthest away from observations. So again, also when you look at intensity distributions, you get better results when you upscale to the GCM field. So it's not just a matter of simple disaggregation, but probably describing better the underlying processes. Again, it's nice to have a metric for this. In this paper, we used a metric called the Kolmogorov-Smirnov distance, which measures the maximum distance between two cumulative distributions. You see this distance is the smallest in the 0.11 runs at all resolutions. So I think this is a pretty strong evidence of added value in present-day precipitation. Now, let's look at climate change. If you have a correction, a fine-scale correction in the present day and in the future, and this correction is the same, for example, your topographic correction, if you do climate change, this cancels out, so you don't see it, right? So what we want to see is a difference between the climate change signal in the present and in the future, in the GCMs and the RCMs. Now, this is, I hope you can see it well, precipitation change. 3 time slices. Let's see, what do we have here? The GCMs, the RCMs, and something that we called downscaling signal. Now, the green is increase, the browns is decrease. So this is the usual signal we always see over the Alps in the summer, decreased precipitation from the GCMs. Now, the RCMs, on the large scale, they have a decrease in precipitation, which, of course, this is driven by the GCMs. But you can see that at the tops of the alpine chain, you can see it also here and here, you have actually greens. So you have an increase in precipitation. So this is a difference. Now, is this added value or is this difference, but we don't know? Actually, you can measure this. You can take something we call downscaling signal, and we calculate this by removing first the mean change over the domain and taking the difference between GCMs and RCMs. Essentially, this is what the downscaling signal that you're getting from the RCMs, positives over the alpine peaks and negative all around. So what is causing this? Do we trust this, or this is just a, I don't know, something that the models are doing? Incidentally, all the dots here mean that all the models are actually having the same signal except for one. Okay, so I think it's 4 out of 5. So this is quite consistent across the different models. So we searched for underlying processes. So if you look at convective versus non-convective precipitation, you will see that the non-convective precipitation actually shows a general decrease, while the convective precipitation has this signal of increase in the large scales, in the high elevations. So essentially, this RCM fine-scale response is due to convection at high elevations. You also see the difference in evaporation. You see a similar signal. Remember this figure because this will be very important. So what is causing this increase in convection at high elevations? There is actually a measure that you can use that is used in weather forecasting. Maybe René used it before, something called the potential instability index, which is the difference in equivalent potential temperature at 850 and 550 millibars. A negative value of this index tells you that you have potential for convection. The more negative it is, the more potential for convection you have. So you see here the difference in this potential instability index, and you see that you get much more negative values, so much more potential for convection over the Alps. This is essentially due to high elevation heating and to a feedback process, because when you actually remove the moisture from the potential instability index, you don't see this signal. So this signal is due to the presence of high elevation low-level moisture and heating that causes increased convection. Now, you might wonder whether this is anything close to reality. And so we actually looked at trends in the last 30 years, well, not the last 30 years, but this period, sort of the last 30 years, in precipitation over the Alps from this EURO-CORDEX trend. And we find something that is very similar to our downscaling signal. So, of course, this is and we would have to go and look at the observation to see whether actually there is more convection happening, whatever. But over the Alps, most of summer precipitation is due to convection. So I think you might say that the signal we find in the change is actually at least consistent with the trends we're finding. You may want to look at other variables. So we looked at R95, extreme precipitation. This is definitely due to convection. You find the same downscaling signal. In fact, in all time slices. I'm sorry, the quality is not great, but I can assure you can find it. You look at temperature, same thing. You see this topographic sort of modulation of the temperature signal, which is something that's been known actually for some time. So conclusion. I think in this paper, which hopefully after a long time may be accepted, it's virtually accepted, let's say, I think we have presented multiple lines of evidence that support the fact that what the regional models are telling us is actually a real added value in climate change. To my knowledge, this may be the only, or at least one of the few cases in which this actually happens. The multiple line of evidence is that, first of all, we get added value in the present day, clear, very strong added value. We have a very strong intermodal agreement. Incidentally, there was one of the 5 models that actually had a very different change signal, but it still showed the same mesoscale signal. So it still showed the same sort of response. We have a plausible underlying process, this increased in instability and convection, and we have consistency with observed trends. So I don't know what else we can say to sort of support the fact that we're actually seeing, I think, one of the few cases of added value in a climate change type of signal. This also, incidentally, is shown by some convection permitting, at least one convection permitting simulation, but it's kind of early to say that. And with this, I think I'm done. Thank you very much.
Yeah, so time for questions. Okay, we have one here. Just wait, please, Elite.
Thank you very much. My name is Ajibo Nura from Nigeria. Sir, in your presentation, you said some RCM can be worse than GCMs because they are worse not because downscaling does not work. It does work. But, sir,
no.
My question to you now is, under the worst case scenario that you have pointed out, could you explain in clear terms the disadvantage of the RCM over the GCM in terms of added value?
Can you repeat the question?
Sir, you said in your presentation, some RCM can be worse than the GCMs.
Right.
Because they are worse not because downscaling does not work.
It's not because downscale does not work.
Yeah, because
I didn't say it's because
they are worse because downscaling does not work.
No, I said exactly the opposite.
Let me get me right, sir.
Oh, okay, you are saying that, not
some
me.
RCM can be worse than GCMs because they are worse, not because downscaling does not work.
Oh, okay, yes, I said this.
Agreed. So if downscaling does work, under the worst case scenario, based on what you have said, could you explain in clear terms the disadvantage of GCM over RCM? That's my question.
Did somebody understand the question?
Okay, but maybe we can move these discussions for lunchtime.
No, I really didn't.
Because basically we have no time for long comments here, sorry.
Yeah, maybe we can talk about this offline because I really didn't understand exactly the question.
So one short question more? Okay. Please.
Yeah. I was wondering about, is it this signal somewhat related with some snow albedo feedback and that grid points that used to have snow, now they have some land and they have more convection? And
yeah, we actually looked into this because over the Alps we do have some snow still in the 0.11 runs, and there is a decrease in snow. I think the snow can be a triggering mechanism. This can be in some ways something that enhances the high-level heating. But the key is the feedback by the moisture. Because when we remove the moisture, the potential for convection increases by very small amounts. You don't see this nice signal. So you have a more warming at high elevation also because of the snow albedo feedback, but then you have this feedback of the moisture that makes more potential for convection. So it has some effect, I think. Of course, we cannot test very much because we would need a run without snow or something, but from what we have seen, it's not the dominant effect.
Okay, thank you, Filippo. So we should move to next talk. It's by Cheng-Ta Chen from the National Taiwan Normal University. So now we're moving to the Pacific region. Can you find it?
Okay. Is that able to control?
Yeah.
So, okay, next one.
Okay.
Where is it?
Just put it back.
Okay. I think the potential of regional change in tropical cyclone frequency track or the intensity has of great interest, and I think it's not only because the associated flooding and disaster, but also because tropical cyclone can also maintaining a regional water resources. But typically the climate model are not been able to resolve this tropical cyclone intensity very well due to their resolution, and also the rainfall extreme associated with it are often not validated very well because, I mean, most of the time they are over the ocean. So here, so this, of course, will raise some of the question on the uncertainty of the future projection from those results. So here I would try to show two examples as to how can we use a high-resolution regional model to kind of improve the tropical cyclone simulation over the Northwest Pacific, and also show actually dynamically downscale projected change can be kind of different from the forcing AGCMs. So as most of you see from the IPCC AR5, it says tropical cyclone intensity and rainfall will be increased in the future. And of course, as I said, that the model resolution are usually, the model used in this assessment is usually underestimating the tropical cyclone intensity due to this coarse resolution, and also the rainfall extreme are not usually validated in any way. And those extreme rainfall are kind of sensitive to the model resolution that we are using, right? So one of the study by people in MRI using MRI AGCM running at a different horizontal resolution from like T95 to from about 280 kilometer match to 20, and certainly, I mean, you can find a tropical cyclone-like vorticity in the coarse resolution model, no problem, but they are far from the realistic tropical cyclone you can find, the structure and the intensity. So this, as I said, that's really the kind of issue we face. So the thing I have is that following this regional climate experiment designed by CORDEX, so I'm kind of using this CMF5 archive, choosing the CCSM4 from it and then use it to drive the regional model I have. It's from ICRC at the University of Hawaii, developed by Professor Wang there. And then the question that we have is, of course, to see how this dynamic or downscaling affect the simulation and also the future projection of this tropical cyclone activities and so on. And so we are also forcing this same model not only with the CCSM4, but also ERA interim for the model evaluation purpose. And then usually this type of study, you kind of objectively do the tropical cycle detection and tracking and try to come up with the statistic of a tropical cyclone. And then here, to compare with observed tropical cyclone best data archive from the IB tract, which is showing on the left-hand side both internal genesis and also the track density distribution over the Northwest Pacific. And then if you look at the two, one is driven by the reanalysis data and the other is driven by the CCSM4 historical simulation. What you will find is that actually the CCSM4 capture better the tropical cyclone simulation. You can see that actually forced with the analysis data, typically underestimated TC number, and also this is formed through field of this tropical cyclone toward the center North Pacific. And that's if you look more carefully through the seasonal cycle of this tropical cyclone over Northwest Pacific, and what you will find that the main problem of this model forced by ERA interim is that during the peak season, that typically this results are kind of underestimated, and it's used as I show that in thermogenesis, you simply don't have the things generally here, but from the observation you do see plenty of this. And the reason that CCSM4 actually produce nice results is just simply that if you have this model during the peak season, you have more moisture in the middle level of the atmosphere, and then you have a somewhat stronger monsoon trough. Then you get the better result. And then, of course, if you look in terms of a model error or bias, but as compared to the reanalysis data, of course, but then this bias actually help to give you a better TC simulation. That's kind of a surprise to us, but anyway. But the other thing we would like to have is, of course, to compare to the original CCSM4 result. But to compare to is kind of a little bit tricky, because if you look at the animation here, one is from the CCSM4, the other is this downscale result, and you can see that, well, this tropical cycle in these two worlds are not quite similar, especially if you have a higher resolution, the tropical cyclone are more compact compared to this large size of a tropical cyclone seen in those coastal resolution models. So how do you do this comparison? It's kind of tricky, but most of the people just use, because the data resolution or data are not the same, and then you have to do some twisting for this parameter using this tropical cyclone detection and tracking scheme in order to do a comparison. So we do that, and then what is the change of the future projection before and after the downscale? And as on the left panel show here, I already illustrated the seasonal cycle, the downscale result from CCSM4 is kind of reasonably produced this seasonal cycle quite well, although somewhat overestimate. But if you look at the using the criteria we typically use for this coarse resolution model, we can only get like less than 30% of the observed tropical cyclone on average. So, but of course, as I said, you can reduce the threshold of detection scheme to increase the number. Here, I'm showing some of this other line there. Try to increase the number from this CCS4 raw data. But you can see that even though you can increase the number, you got quite another problem is the seasonal cycle may not be right. You get a lot of tropical cyclone during the winter. But anyway, so if you look at this increase from original increase of the future projection of this is from TC activity from the CCSM4, what you find is that it increased about less than 20% actually, but for the downscale result, you actually have more than 40% increase. So which one is right? Well, I don't really know, but those are the kind of issue that we have to face when we make the assessment for those the future change of the tropical cyclone. And how about the rainfall associated with it, with the tropical cyclone? So if I take a snapshot of all of the TC tracks along this, and then doing a composite of this, the rainfall center, this tropical cyclone, and for those results that the intensity kind of reach tropical storm or category 0 in 10 atmosphere Simpson scale. And here's the result you see when I do the original CCS4 and downscale result and compared to the trim, and certainly the downscale helped to improve the result. But you can see that if we focus on only those stronger ones, then the coarse resolution may not be that bad compared to if we pick the strong enough. And then, but the other thing you will see that actually the structure, as I said, that those coarse resolution model, which is usually has this maxima rain band, which is further away from the cyclone center compared to the observation. And well, maybe I'm not using enough of resolution. Only even the downscale is only half degree. Okay, so how many minutes I have? 3 minutes. Okay, I don't really have time to go through the second part. The second part is basically quite different setting. We're starting from very high resolution AGCM, 20 to 25 degree, and then we further downscale with this 5 kilo resolution WRF model and nudge with this large scale field, because those AGCM with that kind of resolution does not have a problem to produce a reasonable intense tropical cyclone. But we are interested in the rainfall associated, especially make landfall affecting Taiwan. So, but interestingly, when we do the nudging, we found that the actually original model with the MRI has kind of overestimated the wind speed, and the high rain model, the other high resolution, underestimate. But when we compare with the RCM and AGCM, actually the WRF model actually reduced the overestimate and enhance the underestimate, so make the result actually better. Although in terms of wind speed only, for the central pressure, it's pretty much the same. And also, if it make better actually for the overestimate of the rainfall as well. And also, if you look at this typical rainfall distribution from the observation down to the detail, then the MRI AGCM, although 20 kilo resolution, still have some bias, and worth 5 kilos, that certainly, again, help. And for this tropical cyclone, it does produce those more detailed features that one would like to have for the assessment. Okay, and also this daily rainfall frequency, certainly it also comes closer to the observation compared to the MRI AGCM 20 kilomesh. Okay, and for the feature change, actually, the result is kind of here is looking at the total tropical cyclone rainfall accumulated for average for a year, but because of MRI has some underestimate of the frequency, so compared to your observation, it's weak, and even if you do downscaling, it's still weak. And then for the future, it actually, the further reduction of the frequency leads to actually reduction of the TC rainfall for us. But in terms of the mean intensity, we divide it by the tropical cyclone days, and then actually the intensity increase. And then the intensity for the downscale result is quite similar to observation. So here is my conclusion or summary. So the dynamic downscaling for the Northwest Pacific TC activity from CSM4 to a regional model, it's certainly better simulation find in the higher resolution model, but as I show that climate model bias can lead to actually better TC simulation depends on the conditional. Well, it's just happened for us. But projection change can be quite different before and after the downscaling. And for us, this further downscaling does give us a more realistic terrain-induced rainfall and also reduce the intensity bias and better rainfall frequency distribution and so on. So I'll stop here.
So, one short question. Okay.
Thank you for your talk. I'm wondering if another issue to improve these simulations, it could deal with better atmospheric ocean representation in the RCM. I'm wondering if that could be an issue for getting better tropical cyclone simulations. I don't know if that could be also an improvement for this.
Yeah, I don't know to answer since we are not really running the couple model, and also our resolution is not that high, so that the intensity even from our downscale result is not really that good. But as I show in some of the AGCM, actually they produce the Category 5 tropical cyclone easily, and even kind of a little bit overestimate. And people are wondering whether those are due to the AGCM run produce those results. And if you have a couple model, then the intensity might reduce a bit and to a better result. That certainly, yeah, sometimes can, yeah. But typically, if you have the ocean feedback, then the intensity will actually reduce, not increase. Yeah.
Okay. Thank you very much. So we're moving to next presentation by Melissa Bukovsky from NCAR. So now we're moving to North America.
And how well they're doing or not doing in simulating the North American monsoon. I'm going to focus on a couple of points related to resolution, as well as some comparisons with the NARCAP simulations, on which we've done quite a bit more analysis than for this region as well. Let's see, so the NA-CORDEX simulations that I'm going to focus on here are a couple of the error interim-driven simulations and a handful of the simulations from the 5 RCMs that have done simulations as well, using 5 different GCMs at 25 and 50 kilometers resolution. And I'm going to focus a little bit, if I get to the climate change part of this talk, on the RCP 8.5 scenario. And for this analysis, I'm going to focus on the same periods that were done in NARCAP, which for the baseline is 1971 to 99, and for the future is 2041 to 69. so mid-century. These are some of the simulations that are available for North American CORDEX. We don't have these WRF simulations yet. I put them up here. I'm still working on the ones with the asterisk, and we don't have the data from the others, but I put them up here to show that eventually we will have a nice matrix with 2 different RCMs and 3 different GCMs at 2 different resolutions for comparison purposes. A very brief primer on the North American monsoon, if you're not familiar with it. Like most monsoons, it is defined by a wind switch. A change in the direction to onshore flow during monsoon season. Starting in June, the continent starts to heat up relative to the ocean basins on either side, and the monsoon high starts to form. Really starts down in Mexico and moves northward through the season in July and August, which is the core of the monsoon season. It's positioned on average over New Mexico, at least at 500 millibars. That does move around depending on which level you look at, of course. There's also a heat low that forms over the Sonoran Desert, which also helps turn the winds around. And there's a low-level jet that forms over the Gulf of California here, which also really helps pull moisture into the region, particularly the southwest US. Tropical easterly wave passage also causes moisture surges that force moisture up into this region as well and really dictate bursts and breaks in the precipitation associated with the monsoon. We also have quite a bit of complex orography in this area, 2 terrain features which really dictate the spatial distribution of precipitation of the Sierra Madre Occidental in Mexico and the Mogollon Rim here in Arizona. There. Like I said, there's a lot of complex topography, and this is how it changes with resolution. For comparison purposes, I have up here T85, which is what the CCSM-3 was run at for CMIP-3. It's around 120 kilometer resolution or so in this area. You can see that the Baja Peninsula here doesn't really exist except as 2 sort of island points, and the Gulf of California also doesn't exist. At 50 kilometers, we start to resolve the Gulf of California, which is important. It's at least 4 grid boxes wide through most of its extent, and you can start to pick out and name actual terrain features versus the large anthill over here in Colorado at 100 kilometers. At 25 kilometers, we're really resolving the Gulf of Mexico, which is important, and just for comparison, I threw up some 10-kilometer terrain plots too, so you could see that 25 kilometers is really capturing some of these features quite well. This black box that I've put in here, I've done some area averages, and that's what the area over which those are completed, really focusing on sort of the monsoon Mexican core region of precipitation and what happens in Arizona and New Mexico. Here is what the seasonal average precipitation looks like for this region at a 50-kilometer resolution. I think this was the UDEL data set that I graded here, and you can see the precipitation attached to the terrain in Arizona, as well as the Sierra Madre Occidental. As I mentioned, one of the main features of the monsoon is all of this onshore flow, and quite a bit of that is the moisture flux is dictated by the low-level jet that forms over the Gulf of California here. We also have the sea breeze onshore as well. On average, you should see northerly flow up the Gulf and onshore into Mexico and into Arizona, as we have here in the reanalysis product. We're getting that in the RegCM4 at 50 kilometers and 25 kilometers. You could see that we do in fact have northerly flow here and flow into Arizona, which is important. At 25 kilometers, this is even better represented. The low-level jet is stronger. This is surface flow. The jet peaks just above the surface. But in NARCAP, in the RegCM3, with our NCEP-driven runs, we actually had average southerly flow down the Gulf during the season. You still get the onshore component due to land sea breeze, but if you look at the Gulf itself, on average, the flow is going the wrong direction, which is important really for precipitation in the southwest US. The monsoon in Mexico is more strongly forced. The terrain is there. The precipitation isn't as bad. But when we then talk about the climate change simulations, from NARCAP we learned that half the models got the low-level jet at 50-kilometer resolution, and half of the RCMs didn't. And the RCMs that didn't actually increase the moisture flux away from the continent then in the future. So it was actually drawing more moisture away from the region, whereas the ones that had the low-level jet increased the moisture flux into the region, which really affected then the precipitation projections and their credibility as well, with this feature that you can't get at the coarser resolutions at all. So it's hard to say what would happen then in Arizona in precipitation in the future, exactly if you don't have all of these mesoscale features that we need to simulate the precipitation. This is an annual climatology from the error interim-driven CORDEX simulations that we have so far. The observations are represented here in the black line. You can see that most of the models averaged over this region are actually doing quite well with monsoon onset and the decrease in precipitation in September. Some of them are a little dry, but not too bad. The RegCM4 is doing fairly well, and particularly its 25-kilometer simulation, which is good to see. The spread with the GCM-driven simulations is a little bit greater. You can see that we have quite a bit of excessive precipitation going on. Monsoon onset is captured fairly well. Quite a few GCMs have a problem with the monsoon extending too far into the cold season and being too heavy. They don't propagate the ITCZ south fast enough, or sometimes at all, it seems. The Canadian ESM 2 run is actually providing very good boundary conditions here. Coming out of monsoon season, we don't have this excessive precipitation problem. We also saw this in the NARCAP runs with the Canadian GCM-driven CMIP3 era simulations as well. Some of this heavy precipitation, these two, the yellow and orange line in particular, are coming from the GFDL-driven simulations, which we had a problem with in NARCAP as well. And this is the CORDEX-driven simulations. The spread isn't quite as bad considering what we got in NARCAP then for the same region. We actually have no monsoon precipitation in some of the runs because of bad boundary conditions for this area. And this is the GFDL from that era too. Apparently they share the same atmospheric model I learned yesterday, and they don't propagate the ITCZ far enough south, and there's too much rainfall associated with it, so it forces a standing low just off the coast and just keeps pumping the moisture into the region well into December before that dissipates and moves south. So we're seeing something similar in the new version of the GFDL with the same atmospheric model, but different ocean model. If we look at the RCM4 simulations, which I have the most data from for these runs, we can see that they are always a bit too wet in this case, although they did very well driven with error interim. So this is probably a boundary condition problem. And the big difference here is that the 25-kilometer simulation, particularly in the monsoon season, is always wetter than the 50-kilometer simulation, and this is actually good to see since the low-level jet is better represented and stronger. There's probably more moisture being forced into the region. Part of the problem that's going on in this area average is actually coming from the precipitation that is occurring in Mexico, and there are a lot of potential reasons that this could be the case related to flow associated with the monsoon high or SSTs or the strength of the onshore flow. I'll have to do more analysis to figure out why this is happening. In the 50-kilometer simulations versus the 25-kilometer simulations, I see something fairly encouraging happening over southern Arizona here. We're actually reducing the dry bias that is almost always present in this region south of the Mogollon Rim at 25 kilometers and really getting the precipitation up into that area that should happen. But at 50 kilometers, there's just not enough moisture making it to Arizona. I wanted to mention the CCSM-driven NARCAP simulations because they're a good example of where we've jokingly called useless added value occurs, although it's actually pretty good term for it. Two of these RCMs that are shown in this plot here, the WRF and the Canadian Regional Climate Model, do a very good job with a lot of the mesoscale features for the monsoon. And those features are present in the GCM-driven simulations as well. This includes the low-level jet. But this list here that I have of problems that it's inheriting is essentially negating all of that value. It's the bad boundary condition problem, and it's actually even reducing the credibility even more in the future simulations because we figured out what is driving the changes that are occurring in this model with precipitation, and those are larger scale changes that also aren't credible as well. So lots of useless added value, unfortunately, in some pretty good RCM simulations otherwise. I don't know how I'm doing on time. 3 minutes? Okay. This is the change in precipitation during the core of the monsoon season, just July and August for this mid-century period from the CORDEX run so far. Haven't had a lot of time to dig into the larger scale drivers of what is going on here, or even the mesoscale changes that are happening. Some of them are pretty consistent with what we saw in the NARCAP simulations with or without a good monsoon simulation. These runs that are driven by the Canadian ESM, though, are a little suspect, and I need to figure out more about why they're increasing precipitation so broadly over the western US. This is contrary to what we think might happen with the strengthening of the monsoon high and the increased suppression of convection. So it's possible there's just more moisture making it here, or some other cause that is clearly coming from the GCM in this case. So I've discussed all of that. I guess one of the big points here moving forward for future work is to actually dig into these and figure out what is changing the monsoon precipitation specifically. And it's encouraging that so far none of our CORDEX simulations fail to rain during the monsoon season, unlike with at least half of the NARCAP simulations, because of bad boundary conditions. Here specifically, 2 of those GCMs were chosen because it's known that they provide decent boundary conditions for the North American monsoon. These were chosen by the University of Arizona colleagues of ours that are running some of the WRF simulations. So carefully choosing your boundary conditions for certain things is good, although this doesn't say anything about how they'll actually function as boundary conditions over the rest of the continent. So that's the end. Thanks.
Okay, thank you. So, one short question.
A quick question. Do you have any idea why the RegCM4 had this improved monsoon compared to RegCM3?
I'm going to try to look into that more before the workshop next week. So hopefully I'll have an answer for you then. I want to take a good look at what changed in those 2 versions, particularly, I don't know if any of the dynamics changed, because that would be my first guess, but then we did switch up the physics packages some. Land use too? Okay. Okay. Yeah. Okay. Hopefully I'll be able to answer your question in a week. Thanks.
Maybe just a very small comment, because there are a number of simulations for the Central America CORDEX domain. And this domain now is extended a little bit more northward. So basically, I think it's covering almost entire US. So basically, you can take more simulations, especially focusing on the monsoon in this region.
That would be good too. I guess one of the other things that may have changed is that we did move the boundary much further south here. It actually covers all of Mexico and most of the Caribbean as well. So it should be capturing all of those features like the tropical easterly waves that pass through instead.
Okay, quick question.
Okay, he asked if this was the official North American domain, and for the WRF and the RegCM4 simulations, the domain does go further south than the official outlined domain.
But most of the models actually use a bigger domain than NARCAP.
Yeah, they actually go further east as well.
Does it mean we should change the official North American?
Possibly.
Okay, so we should move to the last presentation. And now it's by Anna Casanueva from the University of Cantabria.
Hello. I'm going to present here some of the results of my PhD that was recently finished at the University of Cantabria. The title of the talk is Added Value of High-Resolution Regional Climate Model Simulations and Comparison with Statistical Downscaling Methods within the EURO-CORDEX framework. The talk has two parts. The first about the added value of high-resolution RCMs, and the second about the comparison with Statistical Downscaling Methods. Please note that with high-resolution RCMs, I'm referring to 12-kilometer resolutions, no higher resolution than that. So first, the motivation of the first part of the talk about added value. We know that there are some studies that claim that the high-resolution simulations are able to better resolve processes related to improve orography and land sea mask. However, other studies claim that there's no systematic or evident improvement of the high resolution. And there are two important things that we have to take into account, because the high-resolution simulations took much more computing power than the coarse resolution ones. And also, there is no unique or best way to assess the added value, as has been already reported in several studies. Regarding the motivation for the comparison with statistical downscaling methods, I will talk a lot about a fair comparison. So first, I need to define what I will mean with fair. First, I will talk about fairness with regard to spatial representativeness, because as you know, RCMs represent area averages, and the statistical downscaling methods can be either developed at point stations or in or with observationals in representing area averages. So we think that the fair comparison should be performed using observational data sets for the statistical downscaling methods representing areal averages as well, to have statistical and dynamical downscaling at the same footing. The second point is related to the metrics that we use for the comparison. So we should use metrics for the validation that have not been calibrated in the training or the tuning phase by any of the downscaling techniques, because it's well known that the statistical downscaling usually calibrate the mean in their training phase. Also, regional climate models are subject to kind of adjustment in the parameterization's tuning phase and so on. And due to the precipitation distribution statistics properties, we know that when we adjust the mean precipitation, all the distribution is scaled along with the mean. So our question here is if are other parameters indirectly adjusted when we adjust the mean in the calibration phase. So we ask these two questions that I will try to give answers at the end. The first one, do the high-resolution RCMs add value with respect to the coarse ones before and or after bias correction? And the second one, is it fair to compare regional climate models and statistical downscaling methods? And this is widely demonstrated in these two papers, which are published already in Climate Dynamics and Climatic Change. So first, the RCM data that I have used is the EURO-CORDEX Serra Interim-driven RCMs, and I'm focused on the Iberian Peninsula and in the Alpine region. For the added value analysis, I consider the simulations at 0.11 and 0.44 resolution, so this is approximately 12 and 50 kilometer resolution. And the comparison of the two resolutions is performed at the coarse scale, which is the skillful scale of the high resolution. Therefore, we are analyzing processes that are solved by both resolutions. These models here are the models that I've used, and these shadow are the ones for the first part of the analysis, those that had the two resolutions. Regarding the observations, I use the Spain 011, Spain 044 for Spain, which are observational data sets for precipitation at exactly the same grids as the EURO-CORDEX RCMs. And for the Alpine region, I use the Alpine precipitation gridded data set, which is a data set for precipitation as well, and it was conservatively regridded from the 5-kilometer resolution into the EURO-CORDEX grids. Here you have the values in winter for the wet day mean precipitation for the two resolutions and for the frequency of wet days. So now I move on to the results. I'm showing here the biases, relative biases, in winter mean wet day precipitation. This is SDII. These are the 7 models of this analysis in rows, and in columns I have results in the first one for the coarse resolution, on the third one for the high resolution, and in the middle these are the results for the high resolution aggregated into the coarse resolution one. So now what we are going to do is to compare the first 2 columns. Okay? And by doing this, well, I am not going into deeper detail on this, but there are some similarities among the different RCMs. Well, some of them, this is a bit more different than the others, but there are some common spatial patterns. But we found that looking at this kind of figures for this indicator and also other derived indicators and to other seasons as well, we found important biases for both resolutions, and that depending on the RCM, the season, region, and the indicator, smaller biases are found in one or the other resolution. So now the question is, where should we look for added value? And then the next analysis is about the validation of spatial patterns. So we consider several metrics to validate the spatial pattern of the 2 resolutions and compare them to the observations. And we have this kind of figures here in this bar plot. I'm showing the number of models from 0 to 7, for which the high-resolution simulations improve on the coarse ones. These results are for the Alpine region in winter, for the 90th percentile on wet days. And these 4 bars represent 4 different metrics related to the spatial pattern, the root mean square difference, the spatial correlation, the ratio of spatial standard deviation, and the bias in the spatial average. The gray zones represent that the results are statistically significant at 5 and 1% significant level. So with this analysis, we found that there is an added value of the high-resolution simulations when they're aggregated into the coarse grid, especially for the first 2 metrics, for spatial correlation and the root mean square difference. And we also find this kind of results for other derived indicators, such as the number of consecutive dry days as well. But now the question is whether these results remain after bias correction, because we know that many people from the impact studies will use these kind of simulations and to correct them. So then we perform a simple bias correction method, which consists on a local scaling, which is correcting the mean wet day precipitation. And this is performed at grid cell level. When we do the same for the corrected data, now we have that there are no significant added value of the high resolution after this simple bias correction method, which we think is an important message to transfer to the impact people. So now we move on to the second part of the talk about the comparison with between RCMs and statistical downscaling methods. In this part, I use, again, the interim-driven EURO-CORDEX simulations at the coarse resolution only at 0.44, and only for Spain in this case. Regarding the statistical downscaling methods, these are statistical downscaling methods under the perfect prog approach, using ERA interim predictors and Spain of 44 predictants in a k-fold cross-validation approach. I built from this work from San Martin et al. That showed the best performing methods for Spain by doing a screening of different predictor domains, variable, and so on. So then the 5 best performing methods in the Iberian Peninsula are these 5 with these predictor variables, which are basically the analog method, the weather types with weather generator, and 3 different combinations of generalized linear models. Now I will present some results for a comparison between statistical and dynamical downscaling, and I will present this kind of tailored diagrams, which are very nice to have at a glance some validation scores of the spatial pattern. So observations are here, so the closer the markers to the observations, the better. You have the dynamical downscaling methods in black and the statistical in red. As the Taylor diagram doesn't have information about mean biases, we introduce this color inside the markers, which is the areal average mean absolute error in millimeters. So from this figure, we found something that we expected from the beginning because statistical downscaling methods perform better than the dynamical ones. But this is an example of an unfair comparison because we already knew that the statistical methods are calibrated to perform, calibrate the mean in their training phase, even this is performed in an annual basis, and these results are only for winter, and even in a closed radiation form, we still have that the statistical downscaling perform better than the dynamical ones that have not been adjusted or whatever with the Spain 044 observations at all. So this would be an example of an unfair comparison because it's something that we already knew. And then we start looking at other derived parameters. For instance, the 90th percentile on wet days. And we found a very similar result. And this is due to what I told you at the beginning, that due to the statistical properties of the precipitation distribution, when we adjust the mean in the tuning phase, we also scale the whole distribution. And we can prove this by only using, again, the simple local scaling bias correction method, which adjusts the mean wet day precipitation at grid cell level. And by doing this simple correction, we go to the point at the end of the arrows for dynamical and statistical methods. And by doing this, we found that the dynamical methods are comparable to the statistical ones. So only by correcting the mean, we can also correct the percentile. So again, looking at this 90th percentile on wet days, it's not fair since this is indirectly corrected due to the relationship with the mean. So then we think that a fair comparison should be performed using metrics that have not been calibrated by any of the statistical or dynamical methods. So then we use the consecutive dry days, the maximum number of consecutive dry days, since this is an indicator that depends on time sequences and the autocorrelation of the time series, and none of these statistical downscaling methods have been trained to reproduce this. And when we get this diagram, we found that there's no clear winner between statistical or dynamical methods, so all of them present some limitations, especially in representing the variability of the spatial pattern and also in terms of biases. So then we also apply here a different correction, which consists on adjusting the wet day threshold for defining a wet day. And by only taking this different threshold, different to 1 millimeter, we have these points at the end of the arrows, and then the spatial pattern and also the biases of the different dynamical and statistical methods improve. Nevertheless, there are still some problems, even after the correction, especially in summer or for different RCMs where the model is drier than the observations. So to conclude, I can answer now these questions. Do the high-resolution RCMs add value with respect to the coarse ones before and or after bias correction? The answer is no in terms of seasonal mean biases in several climate indicators, but yes, there is an added value in spatial patterns. However, this is not statistically significant after bias correcting both simulations. And the second question, is it fair to compare RCMs and SDMs? The answer is no if the comparison is based on percentiles or intensity-dependent indicators due to their close relationship with the mean, usually affected by the method's calibration. But yes, if the comparison considers non-optimized parameters by either RCMs or SDMs, such as the dry spells, as I have just shown. Thank you for your attention.
Okay, thank you. So, one short question. Okay, Filippo.
More than question is a comment about this bias correction issue. Can I say it? Yeah. Well, anyways, this bias correction stuff I think is very how to say, misleading. Of course, if you bias correct 0.11 and 0.44, you essentially bring them to the same observations. So of course they look the same. Or if you bias correct the GCM, it will look the same as a 0.11 model if you're bias correct to 0.11 observations. But when you do a climate change simulation, and for example, you have an effect like we found, where the signal in the 0.11 is opposite to the signal of the GCMs, if you bias correct the GCMs, there's no way you're going to get that signal. So you can bias correct whatever you want, but if you have some feedbacks or some non-linearities, this doesn't add any value. So I think we need to be a bit careful with bias correction.
Yeah, I had to summarize a lot the whole paper, but we discussed a lot about the danger of applying bias correction, and also we only use this simple bias correction, but we saw some indications that if you use more sophisticated methods, then you are doing some things that you should be aware of. So the intention to include them was because impact people is doing this, so just to see what's happening. But yeah, it's clear that the bias correction may have.
Yeah, but I think it's one of hot topics for discussion, basically, about bias correction. Yeah, so it seems, yeah. Okay, so now, okay, one very short question.
It's actually more a comment than a question, really, and probably follow what Filippo was saying. I think also this issue about fairness that you were really insisting, and I've seen all the in this presentation this morning, about all going back to same resolution. It might make sense in terms of metrics and stuff like that, but why are we pushing resolution? Why are we doing statistical downscaling? It's to get to very fine resolution, because we users want that. And I think it's returning among ourselves to do this kind of comparison. We have to think about turning to users and returning information which is relevant to them. So if you can target a point, and at that point somebody is running, you know, a calibration, an impact model, he would be very happy to have that point information rather than a grid average. So you might want to, for your comparison, to do that fair evaluation thing. But at the end of the day, we are pushing resolution because it is demanded. So I think it's somewhat misleading to always go back to higher resolution just to make things fair. We really want to go down to higher resolution because we think there is value there, as was demonstrated by some talk this morning. That was just a comment.
Okay, last question? Okay, but really a last one.
Yeah, interesting presentation. I think we need to look into this really in detail, and I think you do one step which I like, which really applying statistical downscaling both to the GCMs and the RCMs. I think it's not a good idea to apply statistical downscalings against RCMs, because that's really another category of methodologies, and they have another purpose. So the statistical downscaling really removes the biases and goes to even smaller scales. And so I think the proper comparison is to use the same statistical downscalings and applying to the GCMs and the RCM data. And in some of the analysis, you actually do that.
Mm-hmm.
Okay, but it's more like a comment. Yeah. Okay, so now we're finishing, and one more time, thanks to all speakers for this morning's session.